In this video, we will be discussing the polarity of bonds and molecules. Covalent bonding involves the sharing of electrons. However, just because two atoms are sharing electrons does not mean that they are sharing them equally. Some elements pull shared electrons closer to themselves. When electrons are shared unequally, a dipole forms. The element that pulls the electrons closer will have a slight negative charge, while the other atom will have a slight positive charge. The Greek letter delta indicates a partial charge. This is not a full positive charge or a full negative charge. Instead, it represents a charge somewhere between 0 and 1. Because the molecule has two regions of opposite partial charge, this is called a dipole. The prefix di means two, and just like the Earth has a North Pole and a South Pole, this has two poles. Polar covalent bonds occur when there is a significant difference in electronegativity between two atoms. Electronegativity is a measure of an element's ability to attract electrons within a covalent bond. This periodic table shows the electronegativities of various elements, so that you can see an overall trend. Fluorine is the most electronegative element, and it is assigned a value of 4.0. In general, the closer an element is to fluorine on the periodic table, the more electronegative it is. We leave noble gases out of this trend because they typically do not participate in covalent bonding. To determine whether a covalent bond is polar covalent, we compare the electronegativities of the two elements involved in the bond. We subtract the smaller electronegativity from the larger one to find the difference. If the electronegativity difference is less than 0.5, the bond is nonpolar covalent, meaning they are sharing them equally. If the electronegativity difference is greater than 2, the bond is considered ionic. Anything in between is a polar covalent bond, meaning unequal sharing. Chlorine gas, Cl2, is a diatomic element. Anytime an element is bonded to itself, the electronegativity difference is 0. So this is a nonpolar covalent bond. Elements that are far apart on the periodic table are more likely to have a large electronegativity difference. For example, hydrogen and fluorine have an electronegativity difference of 1.9, making the HF bond highly polar covalent. If a metal bonds with a nonmetal, the electronegativity difference is often large enough for that bond to be ionic. This matches what we learned previously. Ionic bonds typically form between metals and nonmetals. For each of the following bonds, determine whether the bond is ionic or covalent. If it is covalent, determine whether it is polar covalent or nonpolar covalent. First, consider carbon and hydrogen. The electronegativity difference is 0.4, so this is a nonpolar covalent bond. When calculating electronegativity differences, always use the absolute value so that the difference is positive. An easy way to do this is always subtract the smaller electronegativity value from the larger one. Now consider carbon and oxygen. The electronegativity difference is 1.0, so these two elements will make a polar covalent bond, meaning the electrons are shared unequally. Next, consider magnesium and oxygen. The electronegativity difference is 2.3, making this bond ionic. Just as we would predict because magnesium is a metal and oxygen is a nonmetal. Lastly, consider oxygen and hydrogen. These elements have an electronegativity difference of 1.4, making the oxygen-hydrogen bond polar covalent. I included the CH bond, CO bond, and OH bonds because they frequently occur in organic molecules. Remembering that CH bonds are generally nonpolar, while CO bonds and OH bonds are polar, can save you a lot of time. Even if a molecule contains polar covalent bonds, that does not necessarily mean that the entire molecule is polar. If the polar covalent bonds point in equal and opposite directions, their dipole moments cancel, resulting in a nonpolar molecule. Consider carbon dioxide and water. Carbon dioxide is linear. Although each carbon-oxygen bond is polar covalent, the two bonds point in opposite directions and have equal strength. This is like a tug of war where both sides pull equally hard. Neither side wins, so there is no overall pull in either direction. The dipole moments cancel, making the carbon dioxide molecule a nonpolar molecule. Water has two lone pairs on the central oxygen atom, giving it a bent molecular geometry. Oxygen is more electronegative than hydrogen, so it pulls the shared electrons towards itself. Because the molecule is bent, the bond dipoles do not cancel. Water therefore has an overall dipole, and this is a polar molecule. For a molecule to be polar, it must satisfy two requirements. First, the molecule must contain at least one polar covalent bond based on the electronegativity difference. Second, the molecule must be asymmetrical, or unbalanced based on its shape. Things that can make a molecule asymmetrical include lone pairs on the central atom or different terminal atoms bonded to the central atom. If a molecule does not meet both of these criteria, it is going to be nonpolar. For example, consider propane. The carbon-hydrogen bond are essentially nonpolar covalent, and a carbon-carbon bond are also nonpolar covalent. And the molecule is highly symmetrical because all terminal atoms are hydrogen, and there are no lone pairs on any of the carbon atoms. Propane is a nonpolar molecule. In fact, all molecules made out of only carbon and hydrogen atoms are nonpolar molecules. We want to be able to quickly look at molecules in order to decide if they are polar or nonpolar molecules overall. Let's look at these three molecules and decide whether they are polar or nonpolar. First is ammonia, NH3. The nitrogen-hydrogen bonds are polar covalent, and there is a lone pair on the nitrogen that gives this molecule an asymmetrical trigonal pyramidal geometry. Ammonia is a polar molecule. Next, consider trichloromethane, CHCl3. The carbon-chlorine bonds are polar covalent, and the molecule is asymmetrical because not all terminal atoms are the same. Trichloromethane is also a polar molecule. Lastly, consider tetrachloromethane, CCl4. The carbon-chlorine bonds are polar covalent, but the molecule is perfectly symmetrical because all four terminal atoms are chlorine. The molecule has a tetrahedral geometry, and the bond dipole moments cancel. Tetrachloromethane is therefore a nonpolar molecule. Here is a practice problem. Decide whether each of the following molecules is polar or nonpolar. For NClO, the molecule contains polar covalent bonds, and the lone pair on the nitrogen gives it an asymmetrical bent geometry. NClO is polar. For the carbonate ion, CO3 2-, the carbon-oxygen bonds are polar covalent, but the molecule is symmetrical because all three terminal atoms are oxygen. The bond dipole moments cancel, so the carbonate ion is nonpolar. For the nitrite ion, NO2-, there are polar covalent bonds, and the lone pair on the nitrogen gives the molecule a bent geometry. Nitrite is polar. Now consider the sulfite ion, SO3, 2 negative. The sulfur-oxygen bonds are polar covalent, and the lone pair on the sulfur gives the molecule an asymmetrical trigonal pyramidal geometry. Sulfite is polar. Lastly, consider carbon dioxide. The carbon-oxygen bonds are polar covalent, but the molecule is linear and symmetrical because the two terminal atoms are oxygen. The bond dipole moments cancel, so carbon dioxide is nonpolar.